Good afternoon, everyone. Good afternoon, Ramakrishna. You have already joined.
Ma'am, very good afternoon. Yeah, I've
Yeah.
joined.
Yeah. Good afternoon, Nishant. So we'll start our session by 2:30 only.
Yeah,
Let's
yeah,
wait for the other participants to join.
yeah. Ma'am. Am I able to make a poll?
You want to make the poll? Okay. So maybe I'll uh, just a minute. I'll just make
Yeah.
you the co-host as well as the presenter so that you can start the poll.
Still, I don't see the poll option.
So in the bottom near to chat,
Yeah, yeah.
the
Yes, now
three
I got it.
dots. Oh,
Now,
okay.
yeah, I accepted. Yes, I got it. Just one or two, nothing to do with your call. You are doing some assessment, right? It's nothing to do.
Yeah.
Good afternoon, ma'am. Am I audible?
Yes.
Okay.
Welcome to National Institute of Technology, Calicut. Leading into the main campus on the left, you can see the old administrative building followed by the new administrative building. These buildings houses the offices of the director and the dean. To the right of the old administrative building, you can see the new creative space sponsored by our alumni. This is where students gather for club activities and evening chit-chats. Leading into the main campus, surrounded on both sides by lush greenery, is the Rajpath Path. Here you can see our hall complex consisting of 3 halls, the Aryabhatta, the Chanakya and Bhaskara, where most of our activities happen. This is the main building, which is perhaps the oldest building of an IT. The main building now houses a few classrooms, the central networking center and the students' grievance cell. Towards the left of the main building, we have the Central Computer Center. The Central Computer Center has around 400 servers and workstations. The Central Computer Center also have a high performance cluster which is capable of 25 teraflop computing. All the major departments are arranged in this quadrilateral. Towards the very left, you can see the computer science and engineering department, which houses labs such as the cloud computing lab, the big data lab, the image processing and multimedia labs, and the machine learning lab. Towards the right of the computer science and engineering, we have the Department of Electronics and Communication Engineering. Some of the major labs of the Department of Electronics and Communication Engineering are the Electronics Circuits Lab, the Embedded System Lab, and the major labs of communication and signal processing. Next, we have the Department of Electrical Engineering. Some of the major labs of the Department of Electrical Engineering
Yeah, once again, good afternoon, all. Maybe we'll just wait for 2 more minutes for the participants to join, and then we can directly start with our session. Yeah, okay. I think we can start with our session. Okay, so welcome all to the third session of the second day, and in fact, this is the first session, from an industry person. So today we have with us Dr. Ramakrishna from the TSI Instrumentation. So he'll be talking to you on the different instruments particularly used for the aerosol measurements. So I invite Ashwini to give a quick introduction about our today's speaker. Ashwini, over to you.
Good afternoon, everyone. Welcome to the next session of ATAL FDP. Theme for today's session is real-time aerosol size, number, and mass measurement instrumentation for air quality studies. For this session, we have Dr. R. Ramakrishna, Research and Analytical Instrumentation from TSI India. A few words about TSI. TSI deals in manufacturing and supplying of precision measurement tools with unsurpassed accuracy and reliability for various R&D domains. For 57 years, TSI has been a global authority on instruments used to measure flow, particulate, and other key environmental parameters. TSI set the standards with the performance measurement tools and precision measurements that they manufacture and distribute to a worldwide customer base. Dr. Ramakrishna is working as Research and Analytical Instrumentation Sales Manager for TSI Particle Instrumentation for past 3 years. He has completed postdoctorate from Karlsruhe Institute of Technology, German, and holds PhD from University of Bern, Switzerland on time of flight mass spectrometry for space applications. He has more than 12 years of experience on analytical instrumentation for various applications. He specializes on time of flight mass spectrometry, particle instrumentation, and atmospheric and geochemistry applications. I take this privilege to welcome our guest speaker, Dr. R. Ramakrishna from TSI India. Over to you, sir.
Thank you, Ashwini and Ashwati. Thank you very much for your nice introduction, and very good afternoon to all. Yeah, now I can share. Hope everyone can see my screen, right?
Your screen
good.
is visible.
Yeah, I'm audible to everyone properly.
Yes, you can
Great.
proceed.
Yeah. So. Yeah. First of all, thank you very much for inviting TSI for this nice, wonderful program. And we will be very privileged to introduce or explain the basic instrumentation or what are the current trends in the instrumentation for the real-time aerosol and aerosol measurements for size distribution, number, and mass concentrations. Because this particular topic is very trendy and very many people are taking this as a very serious issue, and a lot of researchers also doing great work in recent years. And I will start with one quick poll question, so we are all common pace, so we can understand how serious it is. And yeah, just a minute. So if you look at just a minute. So everyone can see this poll right now. So what is the average death rate in India in 2019 due to air pollution? Can anyone guess?
Ramakrishna, I think the poll timing, you have
Yeah,
set
I
it to
said
very,
low,
uh,
no?
you set
It's
it
30
as
seconds.
30 seconds. Okay.
Yep. Yes. Anyway, I can't see, but I will tell you. I don't know why I can't. Okay. See, the answer is almost 4,500 per day. That means almost 1.6 million people are dying in every year due to air pollution alone. This is the WHO statistics from 2019. So you can understand how serious problem it is. And most of the faculties or researchers in India are already taken up. This is a serious issue, and you might be doing a lot. In this presentation, I will introduce, or I will explain few techniques. I cannot explain all the techniques, but I will explain you some of the aerosol measurement techniques and what are the challenges in each and every technique. And also I can in the end I can tell you how what are the instrumentation available for indoor and outdoor air quality studies. So if you look at atmospheric aerosols are very important to understand, because these are impacting directly on atmosphere, air quality, and health of human. There are a lot of sources for the atmospheric aerosols. It can be primary aerosols, it can be secondary, or it can be from biogenic or anthropogenic sources. So we have to understand by studying these in order to study these aerosols, we have to understand physical and chemical properties of these aerosols, so that we can understand the origin and evolution of these aerosols. To do that, we have basically three different types of methods. One, you can do a laboratory study, or you can do modeling studies, or you can go to the field and do the experiments and get the information of these aerosols. So these are the basically three different ways to study the aerosols on the ground. Okay, so if you look at the aerosol sources and the importance, the sources naturally occurring volcanoes or forest fires or aerosols from the sea or mineral compounds or viruses. These are all naturally occurring sources. Similarly, we have sources from the human interactions, either cooking or diesel or industries or whatever with human interference. Also, we have engineered nanoparticles or particles which are from the some kind of when you are working in the lab, also in the industries, you can see a lot of particles are emitting from the this side. So these are called engineered nanoparticles. All these are impacting atmosphere and also the air quality and human health. So basically, if you look at the emissions, we have two major types of emissions, either gases or particles. So I'm not going to talk on these gases. I'll only explain few important techniques for the particles. Most of the times, the particles, there may be from 1 nanometer, which we call it as a new particles, new particle formation it can be from 1 nanometer up to few millimeters. But the bigger particles, more than 5 microns, can easily settle down due to the gravity. So we always interested to know the particle number, size, or mass of the particles from 1 nanometer up to 10 micron. So in general, we always look at PM 2.5, PM 10. That means the particles which are around 2.5 micron are particles about around 10 microns. Okay, so is there any issue, Ashwati? I received one message.
Actually, for me, like I could hear you clearly, but I think some of the participants they are commenting that the audio is low.
Audio is
But
low.
for us,
Okay, okay.
but for us,
No,
it's fine.
no,
Yeah,
it's
maybe
perfect. It's
for
perfect. No problem. It is perfect from for me also. So
Okay.
maybe it was some issue at their end.
Probably you can increase the volume, or maybe I'll try to increase my
oh,
voice.
it's fine
Okay.
from your part.
Okay. So this there are different types of areas of studies. I explained you already. So we basically, in Germany, when I was working in Germany, we did these 3 types of studies to understand the atmospheric aerosols. All 3, laboratory studies, field studies, and model studies. And also, this is very important to understand the particle emissions, and also we have to characterize them properly. Then we can control the emissions by regulating and enforcing with some laws. So this is very important, all these 4 mechanisms. And if you look at the particle characterization, in the particle measurements, we have 2 different ways to measure. Either you can measure in real time, that we also call it as online measurements, or offline measurements. So, okay, I'll explain you what it is. Okay, in offline measurements, we collect those particles in a filter paper, and then we go to the lab and we analyze those particles. In online, you will get a real-time mass or number or size distribution, or also chemistry of the particles. That is those are 2 different ways. Okay, and also these are the 4 major parameters for the physiochemical characterization of the aerosols. People always, or researchers always, look at the particulate mass or particle number concentrations or particle size distribution. Also, people are interested to know about the chemistry of these particles to do the source apportionment. Okay, because these aerosols, even for example, if you take any aerosol from the atmosphere, then it might contain a lot of different chemical constituents inside. So if you look at this graph, so the dust in the atmosphere, the dust alone is contributing almost 73%, and rest is from, major contribution is from the sea salts, and other is from various components, secondary organic aerosols, primary organic aerosols, sulfates, nitrates, and these are all contributing. So one aerosol particle can contain many different types of chemicals. So it is equally important to do the physical and chemical characterization in order to understand the origin or evolution of the aerosols in the atmosphere. Okay, so we can see, where we have different types of methods for aerosol physical characterization. This chart was prepared in 1996 by Professor Pui from University of Minnesota. This was very nice, chart. You can select the right technique to do the characterization of the aerosols. The upper portion, this is for the mass, and second is the number concentrations and the particle sizing. For the mass, we have 2 different methods. One is a direct method and other one is indirect method. In the direct method, it is always works on the first principle, and we don't have any approximations there. For example, in the light scattering method, we first know we will collect the sorry we will count those particles, and then we will assume that the particle density is a 1 and also shape factor is a 1, and then we will convert that particle number into mass. That is one way. Okay, but that is indirect method. Also, for number concentrations, we have different techniques for different sizes, because size is important here to to do the counting. Also for the size distributions, we have various types of methods, which are direct methods and indirect methods. I will explain most of these techniques one by one. Okay, for first, people always know very much whenever you call it, whenever you talk about air quality, they always think about PM2 and PM2.5 and PM10. But there are many other things in that. So for PM measurements, which particulate mass measurements, we have the online methods as a TOM, LP, or QCM, or optical methods. Also, we have some offline methods by collecting the sample and in the filter paper, and we can do the analysis. Okay, and for the particulate mass measurements, so if you look at this graph on the right side, the top portion is for particle number versus size distribution. And also here, the bottom one is particle mass versus particle size. So the first, this portion tells you how many particles are in the below 0.1 micron. That means below 100 nanometers, how many particles are there in the atmosphere. Also, how much mass is contributing. So if you look at the number, it is very high compared compared to the bigger size. But whereas the mass is very, very less. That means the mass of the nanometer particles is very, very less, and it is very difficult to measure. Whereas the bigger particle, though they are in very high in number, and they contribute very, very, very less mass at the higher sizes. So why I'm telling this is, people always look at PM10 and PM2.5, but there is also equally important for the PM1 and also the number of those smaller particles. So we have to do the carefully when you are doing any air quality studies. Okay, so as I mentioned, the nanoparticles mass measurement is very challenging because they are highly diffusion in nature and contribute very low mass to the total mass of the particles. And also the humidity effects is very, very difficult to manage. Okay, and if you look at the different methods, so this is this very standard and very old method to do the particulate mass measurements, that we call it as a federal reference method, gravimetric method. So this is, we put a filter paper on this, inside this, and we, with certain flow, we collect the we do the experiment for 24 hours, and then we collect those filter paper, and we can check how much mass is accumulated on the filter paper. This is this is a standard method actually, but this is very laborious process and time consuming process. And if there is a very little change in the humidity, the filter paper will destroy, and you cannot collect properly, or you cannot estimate or measure the mass properly. Also, there might be possibility for the potential chemical reactions on the filter paper. So these are all pros and cons for this. This is very simple, but the artifacts are a lot in this method. Okay, and another method for the PM measurements is beta ray attenuation method, which we call it as a BAM or EBAM. Yeah, in recent days we have different types of BAM instrumentation. Okay, this is also a FRM method, and in this we have beta rays focused on the filter paper. We weigh the filter paper before, and then we can check the beta ray attenuation over the period of time. The particles are accumulated on this filter paper. The attenuation of the beta ray particles will increase. The attenuation is proportional to the inversely proportional to the mass of the particles. So we can estimate the total mass of the particles based on the attenuation. So in this also, this method is always overestimates PM2.5 because it cannot take temperature, pressure, and relative humidity into account, and the temporal resolution is also very, very less compared to other latest methods. Okay, yeah, and there is another method, very standard method, which is old one. We call it as a high volume or low volume samplers. In this method, we have a filter paper here, and then we pull the air from the outside with a vacuum pump, and then those particles from a certain size, or maybe actually this is a total, it collect the total suspended particles collect on this filter paper. maybe for 24 hours or 48 hours, depending on the experiment. So then we can see how much mass is loaded on this. So this is also does not take care of the relative humidity and other parameters into account. There will be a lot of errors in these measurements as well. Okay. And we have another very standard method, which is called as a tapered element oscillating microbalance method. This is also one of the FRM methods. In this method, we have an oscillating tapered element, which is in between two magnets, and it always vibrates with a certain frequency, which is natural frequency. Whenever a particle fall in on this tapered element, then the vibrational frequency will change. The change in the frequency will be recorded, and also it will be directly proportional to the total mass accumulated on the tapered element. In this, also we did not have any control on the humidity. Why I'm talking every time on the humidity is because when even there is a small change in the humidity, the particles will coagulate, and also the mass will increase or decrease based on the change in the humidity, relative humidity of the atmosphere. So it is always important to have controlled environment for the particulate mass measurements. Okay, and also the frequency, the data frequency is also very less in this method, but it is one of the standard methods in the USA and also other countries. We have another method, very direct method to measure the particulate mass for the both ultrafine particles and also fine particles, which we call it as a quartz crystal microbalance microorifice uniform deposition impaction method. This is one of the direct mass measurement methods. In this, actually, this is a combination of two different techniques. One is quartz crystal microbalance, and also Maudie impaction method. So what will happen is in this kind of methods, we have particles are coming pulling from inside with certain flow rate, and those particles will be the particles will be the humidity and temperature will be controlled inside, so that there won't be any artifacts due to the relative humidity and temperature, and those particles will be fed to the impactor, which is a Maudie impactor. In this Maudie impactor, the bigger particles will settle down first, and then smaller particles, and then smallest particles on the bottom. This is one of the best techniques for the ultrafine and fine particles mass measurements. Even it can sense the 50 nanograms of the particles. And you can look at this. I'll explain you the principle. So the Maudie, the quartz crystal plate looks like this, and it always vibrates with a certain natural frequency. Whenever there is a particle fall on this, then there will be a change in the frequency. That change in the frequency is directly proportional to the mass. So that means it is working on the first principle. So it doesn't require any calibration or something. So like that, we have 6 different we'll have 6 different stages, and you can measure from 2.5 microns to 45 nanometers. Okay, and you can see the result of this kind of equipment. It can detect from the atmospheric mass concentrations in 6 different channels at very high temporal resolutions. Even a small change it can detect. And this is a comparison between TAOM method and QCM method. You can see the QCM method, which is in red color, has very high resolution compared to the TAOM method. We have another technique that direct. It's actually it's also a direct technique. Sorry, it's an indirect technique based on the electrical low pressure impaction method. So in this, we have impactors at many different stages. from 1 nanometer up, 10 nanometer up to 10 micron or something like that. So in each stage, these are connected to the these impactors are connected to the Faraday cups. So Faraday cup basically measures the charge on the particles, and that means it counts the particles and then it converts into the mass. This is indirect. That's why we call it as an indirect mass measurement method. But this is a very nice technique. It can cover a large range, but the problem is these electrometers are very, very sensitive. Even the small change in the sampling line, it will vary the result. So it is not very accurate, but it can cover large size range. And we have another method which we call optical methods, which are very popular in the field of particulate mass measurement field. So in this we have two different techniques. One is single particle light scattering method, and the other one is light scattering photometry method. In single particle light scattering method, so we pull the this instrument pull the particles at certain flow rate, and those particles will be shooted by a laser, and then the light scattering will be detected by the photometer, and then this photometer, based on the intensity of the photometer, we can tell it is a 1 micron particle or 2 micron particle or 10 micron particle. So this counts basically every single particle and then convert the particle into mass. So there are assumptions. We have to assume the particle density and particle shape as a spherical, and particle density as a certain like 1 or 2, 1, whatever if you want, based on your calculation. So it will convert into the mass. It's also indirect method, but it's a very cheap method and very, very popular method in the field of particle mass measurements. Yeah, and there is another method which is also light scattering method, but based on the photometry. In this, the difference is, for example, if there are two particles comes at a time, there will be a lot of there will be artifacts in this field. It cannot detect as a single particle. So for those kind of applications, for example, if people who are working in the field of engine emissions or some other applications, this single particle light scattering method is not applicable there. So we have to use a photometry method. In the photometry method, it collects the light scattering from the volume of the from a volume of the particles, and then it will based on the some electronic and also the optical adjustments, we can measure PM1, PM2.5, PM4, and PM10 measurements. This method is very suitable for high concentrations, where we can see very huge number of particles in the atmosphere. Okay, and those are the methods which are with which we can do real-time mass measurements, and we have some methods with which we can do offline measurements. So this the most important method is cascade impactors. In these cascade impactors, the impaction technique, I think you might be known about this impaction method. So we have a vacuum pump here, and we have a different stages of the impactors. And we pull the air from the outside, and based on the inertia of the particles of the bigger size will settle down first, and then the next size, smaller size, and then the smallest size on the bottom. So this is based on the principle of inertia, and this also works on collect the particles based on the aerodynamic particle sizing. So we have two different types, either Maudie impactors or Anderson impactors. So in the Maudie impactors, the cut size and collection of these particles very, very accurate compared to the Anderson impactors. In the Maudie impactors, if, for example, if two particles with 5 microns and 6 micron coming at a time, there might be chances that both are settled at one stage. But in that we call it as a cut point. So the difference between the Anderson and Maudie impactors is very, very clear, that the Maudie impactors cut points are very accurate. And these once we collect the mass on these filter papers, and when we have to do the weighing pre-weight and post-weight of these particles, and also we can use those filter paper for the further chemical analysis. Okay, So this is the same which I explained. This is the cut point curves. You can see the one curve should not interfere with other. That we call it as a collection efficiency of the each impactor. So Maudi impactors have much better collection efficiency compared to the Anderson impactors. Okay, for number concentrations, we have three major different methods. Most of the people will do counting on the real time. Nobody will do nowadays on the offline methods. In the real time, we have three different methods. One is condensation particle counting and electrometer technique and optical particle counters. So these three are the major methods. And also, as I mentioned earlier, size matters in particle counting, because one single method cannot do entire particle counting of the entire size range. So we have to people always use for particle counting light scattering method, because it's a cheap and very easy to do that. But the problem is light scattering method cannot work properly for the particles below 300 microns. So for those particles, we have to use some other different technique, which is a condensation particle counting technique. So in this, what we will do is the instrument will pull the sample air from the outside with certain flow rate, and then the particles um, uh, will go into the saturation region. I'll explain here. Yeah, saturation region. And in this region, we will have a saturator. Mostly we use a butanol or water as a saturator, or isopropanol. And these particles will, so the saturator, we will heat the saturator liquid, and then the fumes of this saturator will be condensed on the particles. And then then immediately the particles will be pulled into the condenser region. In this region, the fumes of this saturated liquid is condensed, and then it will the particle size will be increased. So this is called condensation method. So then whenever the particle size is more than 300 nanometers, it can easily detected by the optics. So at the end, it will be detected by the optics, but the basic principle here is the condensation. So that's why we call it as a condensation particle counting. So whenever if you are looking at a particle counter below 300 nanometer particles, you have to go for a condensation particle counting method. Okay. And there is another standard method which is used on the first principle. This is an electrometer technique. So in this, we have a Faraday cup which measures the particle, the current on the particle based on the charge and the particles. So if you look at this equation, you have a total number of the particles is proportional to the charge, charge and the particles. So that means each particle contains a charge, either positive or negative charge on the in the atmosphere. This charge can be detected easily by the Faraday cup. Even for femtoamperes of the charge can be detected by this Faraday cup. But the problem is, though it is very standard method to do the calibration of the condensation particle counters and other particle counters, but this is very, very sensitive. You have to use it very carefully. The very minor changes can change the results. And another method is optical particle counting method. So I mentioned earlier, we have here, it is same as a single particle counting. We have here a pump which can pull the particles. And as I explained earlier, we shoot with a laser, and then the photodiode will detect the particles, total number of particles in each particle. So it can count the particles based on the number of signals. Okay. But for particle counting, there won't be any issue. But the problem is with particle sizing. We will have a lot of assumptions in this. Okay, and for sizing, which we call it as a particle size distribution. So for particle size distributions, we have different methods: electrical mobility principle, or optical methods, or QCM methods, impaction methods. So in the and also for offline, we have, as I explained earlier, the impactors can do the same job of particle sizing. Okay, why the sizing is very important? Because if you look at for some of the aerosols in the atmosphere, for example, welding fumes can be in the range from 10 nanometers to 10 micron, or smoke particles can be from 10 nanometers to 100 nanometers, and also bacteria can be from 20 nanometers up to 10-20 microns. Also, virus will be from the range of 10 nanometers to 100 nanometers, something like that. So in the atmosphere we will have very wide range of aerosols and in terms of size. So in order to do, there is no instrument that can do sizing of entire range. So we have to select the instrument for the sizing based on our application. So for example, if you look at electrical mobility principle, we have two different methods. Scanning mobility particle sizing spectrometer method, or fast mobility particle sizing method. So in the scanning mobility, we can measure the particle size from 1 nanometer up to 1 micron, but it is a scanning process. It cannot do immediately. It will take time to do the complete scanning from 1 nanometer up to 1 micron. So it takes at least 1 minute to 6 minutes or something. But it is and the other side, we have a fast mobility scanning method. That is, it's not scanning method, it's a direct sizing method, which is based on the electrometer principle. So in this, we will get data point of every 0.1 seconds. It is highly recommended for the highly dynamic environments, for example, engine exhaust studies. So I'll explain you the principle and other things for the scanning mobility particle sizing for the air quality studies. So this is the gold standard method for the aerosol size distributions of the nanoparticles. So we have here actually this scan SMPS, we simply call it as SMPS, includes three major parts. One is we call it as a classifier, and second part is a differential mobility analyzer, DMA, and other part is condensation particle counter. So in this, we pull these particles with a pump, and then these particles will be neutralized here, and then it will make actually a single charge, and then those particles will be pulled into this differential mobility analyzer. Based on the charge on the particle or size of the particles will deviate one at a time. So for example, if there are 1, 5, 10 nanometers, first it will come 1 nanometer particles, and then 10 nanometer, and then 5 and then 10 nanometers. So the sizer, this part we call it as a sizer. So this sizer will give you one size at a time. And then these particles will be counted by a condensation particle counter. Earlier I explained what is a condensation particle counter. So so the instrument looks like this. So here is the principle of this electrical mobility principle for the SMPS, scanning mobility particle sizers. So based on the size of the particle, the particle will deviate in the electrical field, and this electrical mobility is depending on the size of the diameter of the particles. Okay, and so this method is very useful for nanoparticle sizing. It can measure particle size from 1 nanometer up to 1 micron. But if you want very high frequency data, as I mentioned earlier, if you want a data point for every second, or the complete spectra for every 1 second, then you have to go for a fast sizing methods. So that we call it as a fast mobility particle sizer, FMPS. In this method, instead of the differential mobility analyzer, we have a high voltage electrode here, but on the other side, we don't have any condensation particle counter, but we have Faraday cups here. And these Faraday cups measures the total number of the particles, and also these particles will deviate based on the particle size. So this is based on basically on the electrical mobility and electrometer method. And you can these kind of instruments are very useful for highly dynamic areas. For example, if you are doing any combustion studies or doing any engine exhaust measurements, this kind of instruments are very useful and tells you how the for example, people use this equipment in the field of engine exhaust studies. When people are developing any engine, they can check the particle number concentrations immediately at when there is a change in the a minor change in their development, and also with respect to the different fuels. So you can see the change in the particle size distributions so that you can make it better. Okay, and so the most important things in this nanoparticle measurements is so the size distribution measurements are very difficult due to the diffusion losses and also electrostatic depositions and also thermophoretic effects. So you have to, if you want to measure nanoparticles properly, you have to use the sampling probe as close as possible to the instrument. And also we have to avoid metallic tubes, which leads to the electrostatic losses. And also the temperature gradients will change the results. You have to keep in mind when you are doing any nanoparticle studies. And the second method for the sizing is optical particle sizing. So most of the optical counters will also give the size. For example, if there are 100 particles coming at a time, so this particle counter will measure the total intensity of the light scattering through the photo detector, and then that will also tells you what size it is, and then it will differentiate, it will group the particles in different channels. So that basically the optical particle counters, most of the optical particles will counters will also do the sizing. So in these you can see for example, one of the optical particle sizes will give particle sizing from 0.3 microns up to 10 microns, which is standard range for the atmospheric aerosol measurements. In this, so they always starts from 0.3 microns, because below 0.3 microns, optical techniques will not be very useful because of the very low intensity from the light scattering intensity from the laser light. So the photodiode cannot detect accurately. So you can see this is one of the experiments done by my colleagues in Germany. So in the New Year event, they can see the total number of particles are increased at different. This is for the PM10 actually. Sorry, yeah, PM10. PM10 concentrations are increased. We are as I mentioned earlier, particle counters can give particle size, number, and also it will calculate the mass. That's why I mentioned it here as a PM10. So it will give PM 2.5, PM10, and PM1 also. PM1 means from 0.3 microns up to 1 micron. Okay, and it will also it will give you the data of for each and every second in multiple channels. For example, some comes with 6 channels, some with 12, or some with 16 channels. So in 16 different size channels, you will get the total number of particles and also size of these particles. Okay. Yeah, and these are very portable equipment, and we can take it to wherever you want, and they are very useful for indoor and outdoor air quality studies. The only fear factor is we will have two assumptions here. Basically, because the light scattering is depending on the refractive index of the material. That means material to material, the light scattering intensity will be changed. So we have to be very careful and and at which locations and what we are sampling. And also the size, it always assumes as a one. Sorry, shape factor is a 1. That means it's always assumes as a spherical particle. But in the atmosphere, in reality, we will have very different types of shapes of the particles. So if you want to measure more accurately, then you have to go for a different technique. But in general, light scattering method is the cheapest method, and you can measure particle mass, size, and number at a time. Okay, and another gold standard equipment for the larger particles. Now, so far we have we have seen nanoparticles, we have scanning mobility electrical mobility method, and for bigger particles, we have optical methods. If you want to measure even bigger particles, for example, up to 20 microns with a more accuracy, and also with a more number of channels, you have to go for a aerodynamic particle sizing. In the aerodynamic particle sizing, why we call it as aerodynamic means in the atmosphere, all the particles will follow the aerodynamic path. So, for example, even if it is a irregular shaped particle or with a different densities, the particles will have a same settling velocity. That we call it as a aerodynamic diameter, because the particles with the different densities or different shape factors, it doesn't matter what kind of what density it has, and also what diameter it has. But if particle has the same settling velocity, then we call it as a aerodynamic diameter. And all the particles in the atmosphere, when you are measuring any air quality studies, they follow aerodynamic path. So it is more appropriate to measure aerodynamic diameter instead of optical diameter or any other diameters. So that will tell you that will give you a more accurate results than any other method in the in other technologies. So I mentioned here the particles will follow this aerodynamic method here. Yeah, see, particles exhibiting the same airborne behavior have the same aerodynamic regardless of the physical size, shape, and density of the composition. So you don't need to assume when you are measuring aerodynamic diameter. Okay, and yes. So if you look at the principle, the time of flight principle, that means instead of one laser, we will have two lasers. Our laser with a beam splitter, we will have two laser beams. And when particles, particles cross these two beams, we will have two signals. So the distance between of these two beams is fixed, and the time of flight, that means the time to traverse from one beam to other beam, is directly proportional to the particle size. So the smaller particles can travel quickly, and the bigger particles will take time to reach the other beam. So that's why this calls the time of flight. So in this method, there is no assumptions. Everything is clear here. We don't need to worry about the size, shape, or density. So in this method, we can get more accurate results compared to any optical method. So this is the schematic diagram, and don't need to. So for example, if you want to get more accurate data from atmospheric aerosols for air quality or any other applications, you have to go for aerodynamic particle sizer, or if you want a rough estimation, then you can go for optical particle sizing, or if you want more the smaller particles, then you have to go for scanning mobility particle. These are the three major types. Okay, and we have another offline method. This is impaction method. I explained you already. In this we can also get particle sizing from 10 nanometer up to 10-20 microns. We have different types of models which can with the different size channels. For example, if you want 3 impactors or 5 impactors or 10 impactors, you can choose, and you can do the more accurate size distribution measurements with the impactors also. But it is a time consuming and offline method. And I mentioned that chemistry of the particles is equally important besides this mass, number, and size distributions. So for chemistry, we have majorly 3 different types of methods. I will say only 2 methods, but all these belongs to either mass spectrometry or spectroscopy. So in the real-time aerosol mass spectrometry is the very popular technique for the chemistry measurements. All are based on the time of flight instrumentation, time of flight mass spectrometry. And in these, we have 3 major types. One will be now single particle mass spectrometry. That means it counts, it measures the particle chemistry of every single particle. The other method is chemical ionization method. In this method, we will have this will give the chemistry of the all organic component of the aerosols. And the other method is for the bulk aerosol methods. It will, in this method, we will have the chemistry from, we can get the chemistry from the multiple particles, not from a single particle. This is also limited to organic and inorganics. Okay, I'll explain you how it works. So in this, we have a aerodynamic lens which will focus the particles from the inlet, and those particles will be very streamlined, so that we will make sure that there will be one particle at a time. So there are two laser diodes, which is very similar to time of flight method. So each, whenever there is a particle crosses through this laser, there will be a signal, and each we will get two signals. And then when particle crosses the second signal, then it will trigger the laser, the big laser. That laser, we call it as examine laser, will shoot the particles, and it will ionize all the particle in species in the particle, so that the whole particle will be ionized. In this, we will get organics, inorganics, and refractive material. That means if there is any metal inside of the particle, due to the high intensity of the laser, it will also ionized. So that in one single shot, we will get all three component, all three organic, inorganic, and also metal composition of the particles. So for example, you can see here, for if you feed any sodium chloride particle, it will give you ions of sodium chloride, sodium and chloride. So it is also having positive and negative ions. So you will get complete information of the particle. But the problem is the particle sometimes will not ionize completely due to this is a very small space. So particles sometimes may not very completely. You cannot get the composition of the whole particle. That's why we call it as it's a very highly qualitative but less quantitative. And another popular method is aerosol mass spectrometry, which is widely used in the field of aerosol chemistry. You can widely used for aerosol air quality studies as well. And with this kind of equipment, in this both the methods, we will get particle number and also size because of this time of flight region. So in this method, in the bulk aerosol mass spectrometry method, so the particles will feed through feed to this aerosol vaporizer section, and these particles will be vaporized with the thermal vaporization method and ionized with the electrical ionization method. So in this electrical ionization method cannot ionize the refractive materials. It will only limited to organic and inorganic. Still, it is good, but yeah, I mentioned earlier, each method has its own limitations. Okay, and we will get the chemical composition of these particles by ionizing this. So this is in India we have 3 or 4 equipment like this in IIT Kanpur and IITM Pune. This is and also PRL has one of these equipments. And the other method is spectroscopy method, which we know people collect the particles and you can do the XRFRA, ICP-MS elemental analysis. Nowadays, some of the there are some limited elemental analysis XRF instrument also available. For example, if you want to measure lead or some other metals, it will measure the metals in the aerosols. Those kind of equipments are also available now. And another popular method in the field of aerosols is black carbon measurements, which is basically measures the total total carbon particles in the atmosphere. So this is also attenuation method. So we have a filter paper here, and the attenuation of the rays will be the light source will be attenuation of the light rays will be increased over the period of time due to the collection of the carbon particles. So this is another method which is widely used to know only the black carbon measurements. Okay, so with these, I have explained the major techniques available right now with for mass, number, and size distribution, and also chemistry. Now I'll show you some examples how we can use these equipment for the indoor and outdoor air quality studies. So if you look at the WHO document, so we can see the almost 40% of heart diseases are due to the outdoor air pollution, and also these are all statistics we are very well known. And we on one line, if we can say that both outdoor and indoor air pollution is dangerous, we have to have a mechanism to identify where the pollution is, and we have to have a mechanism to control it. Okay, and these are some of the examples. We might have gone through this kind of diagrams a lot in the last presentations, but in this, what I can say is if particle size is more than around 10 microns or above 2.5 microns, they can go to lungs. Even if it is less than 2.5 microns, then even they can go very deep into the lungs, and also they can go to the penetrate to the blood, which is very, very dangerous. And most of our measurements in India are only either PM10 or PM2.5. Very, very less number of people are working in the nanoparticle studies are also below 2.5. And also the people whoever working on the measuring this PM10 and PM2.5, so they always do without any proper care of the relative humidity. So I'll explain you one by one. So if you look at the sources, there are multiple sources for this outdoor and indoor, either from the transportation or waste management, or for the indoor we have different types of indoor air pollution sources, also agriculture's part, and also dust, natural, and also I will say primary and secondary sources. So and Lung Care Foundation has summarized very nicely these pictures. Lung Care Foundation from New Delhi, they are doing a great job in the field of they are creating a lot of awareness for the public. So you can see the different sources for the outdoor air pollution and also indoor air pollution. I'll come to first indoor air pollution here. So we are spending a lot of time in the indoors for sure, and the indoor air can be almost 5 times more polluted than outdoor, which we never realize. We feel it as a normal, and and these particles, the indoor air is often affected by the outdoor air because we have some sources inside of the air, inside of the house. For example, if you look at this process, we have a lot of internal sources, and then we have some external sources from the outside air. Both are creating more and more sources for the indoor air pollution. Moroska has nicely summarized in this paper how these indoor pollution is increasing for at different places in indoor environments. For example, at home, or in the school, or in the offices. How this indoor air pollution is, how the particle, basically 3 different particle types, either mass, number, or size, how it is changing. That is, he nicely summarized in this publication. And we can, in the recent days, we have seen a lot of publications, a lot of governments also. For example, German government in the month of November, they issued some regulations for the ventilation and humidity, and also filtration, how it should be in the public offices and also at home. They made some guidelines, and they released some documents so that we can reduce the virus transmissions or particulate. Whether it is a bioparticle or nanoparticle, they always create a lot of trouble for us. So we have to we can manage this particulate pollution inside the house or home or office or indoor by controlling these three: ventilation, humidity, and filtration. Okay, and Marask, in this same paper, he also explained how a particle number and PM10 and PM2.5 is increasing and decreasing, and where the sources are coming from. This orange one is inside the house. That means we can see more number of particles from the household itself or indoor itself. Or due to the outdoor air, we can get a lot of PM2.5 and PM10. PN always tells you uh, how uh, uh, how many smaller particles are there in the atmosphere, because we never care about the particle mass for the PN below 2.5 microns. And also in the school, there are more number of particle numbers are contributing to the school atmosphere compared to the mass. And also in the offices, we have all the three are coming from the outside. So like that, if you want to analyze carefully where these sources are coming from and how these parameters, particle mass, number is changing, you should have a proper instrumentation for that. And my colleagues in Germany, they did funny experiments during the last lockdown. He measured how many particles are emitting inside the house at different areas, kitchen or living room or in the bedroom, with some actions. For example, if you are using your microwave, how many particles are getting released, and also when you are using cooking, when you are cooking or ironing, how many particles are coming out. And also when you are having any heating system inside the house, how many particles are releasing. They measure very nicely. You can see one example here: before starting of the oven and after starting of the oven, how many particles are coming out. Almost 25,000 particles are coming. This is a huge number. They affect our health. So also this now how many this you can see how these particles are changing with respect to the time. And in collaboration with ISR Bhopal, Dr. Ramesh Sundaran, we did one experiment, one study in the rural areas of Madhya Pradesh. So the team has used TSI equipment. So here you can see the MODI impactor, the QCM MODI impactor, and OPS, and also some black carbon measurement equipment, MAGI equipments. So they measured the particles coming out of the cooking stove with the different fuel types, for example, cow dung or wood, and also crop burning, crop waste. So how these particles are, how many particles are coming out, and what is the exposure rate to the children and also to the adults. They nicely summarized that with a simple experiment in this study. And if you look at indoor air quality monitors, TSI has a lot of varieties of the equipment. For example, if you want to study both gases, I haven't mentioned and explained anything about the gases in my presentation, because that's not my portfolio or my expertise. So, but TSI does have equipment for the mass and gases. In gases means CO2, ozone, and some other formaldehyde and some other critical gases. So TSI has these equipments. This Q-Track can measure both PM 2.5 and also some gases. And Dust Track, this is a very portable equipment, and it can measure PM 2.5, 10, or any one at a time. And we have also a personal exposure monitor. For example, if people who are working in the field of in the industry or any mines or some other places, they can wear this in the pocket, and then with some tubing, you can see how much exposure you are having when you are working in the harsh environments like industries or in the mining areas. Also, we have to measure the particle number. We have instrument called P-Track. It will measure particle total number of nanoparticles. means from 10 nanometer up to 3 microns. It will give you total number concentration. And also we have another instrument called EVM 743 for PM and different types of gases. And for example, if you want to use any instrument inside your office, how your air quality is, if you want to it's a kind of simple wall-mounted equipment. You can see how the PM 2.5 is changing with respect to the time inside your room. So these are the equipment, and I will play a small video for the Q track.
Ramakrishna, is there any audio for that?
Oh, you
The
don't have,
video?
you don't feel you don't have
No,
audio?
no.
Okay, sorry. 1 minute, please.
Okay.
Now, can you hear?
Yeah, it's fine.
Good, thank you.
Studies have shown that we spend 90% of our time indoors. Scientists are now finding that indoor air can be up to 5 times more polluted than outdoor air. The quality of the air within our schools, office buildings, manufacturing plants, and other public spaces can directly impact our health, job performance, and learning ability. New technologies and the advancements in building materials and furnishings have changed the dynamics for evaluating indoor air quality. IAQ professionals are seeing a demand for more versatile, investigative tools to help them conduct indoor air quality investigations. To effectively monitor indoor air quality in today's high-performance building environments, you must be able to measure a wide range of parameters. It's important to assess potential sources of air contaminants and determine the proper amount of ventilation to provide your building's occupants. Measuring your indoor air quality has never been easier with the Qtrack XP Indoor Air Quality Monitor. This monitor is a field expandable instrument that simultaneously logs standard IAQ parameters, along with the mass concentration measurements and 6 different types of gases. This flexible, lightweight instrument can be configured, customized, and expanded to meet the increasing demands indoor air quality professionals face. The Qtrack XP Indoor Air Quality Monitor was designed with flexibility in mind. Pick and choose the sensors you need and simply snap them into place. You can also swap out the entire sensor module for another preset module. Each sensor can be quickly replaced and calibrated in the field, giving you on-the-spot control over survey parameters. The removable sensor module reduces downtime for service, so you can keep your Qtrack monitor running without interruption. The large touchscreen display makes it easy to scroll, select, swipe, and zoom, making streamlined workflows and field calibration a breeze. Wi-Fi connectivity allows you to download data remotely. The Qtrack XP Indoor Air Quality Monitor expands your IAQ measurement capabilities, one sensor at a time. To learn more, visit tsi.com/Q-Track-XP.
Yeah, that is about Qtrack, and I will explain you some of the things for the outdoor air quality studies. And in the outdoor air quality studies, we majorly have 4 different types of methods. Either you can use a mobile air quality studies, or you can go for a field and do some experiments, or you can use some unattended air quality monitoring network, or you can do laboratory studies. So in these, here you can keep all your equipment, and you can make one container, and then you can go around and do the mobile air quality studies. And in the continuous air quality monitoring network, nowadays we can see a lot of buzz on the low-cost sensors or other continuous air quality monitoring stations, which measures PM2, PM2.5, and also it will calculate air quality index. Those kind of will be with some network. It will measure on different locations, and due to the with the cloud, you can get the data. You can visualize the data at different locations. Also, you can go to if you can set up, for example, if you want to measure anything at the mining sites or at different locations and the high altitude sites, then you can install your equipment and you can do the field studies. And also you can do some laboratory studies. And for these, for outdoor network studies, TSI does have equipment for a wide range of equipments. You can say like sensors to high range research equipment. For the sensors, we have something called Blue Sky, which is recently launched. And the other one is environmental dust track, which we can keep this photometer dust track inside. And then we have also have a control of relative humidity and temperature, so that the measurements will be more accurate compared to any other method. And we also have optical particle sizer that you can install outside, and you can measure continuously 24/7. So these are all for the network. And for example, if you want to carry the equipment, and you can do that if you want to do the experiments, and then you can use these different types of equipments, which dust track can measure PM1, 2.5, PM4, and also PM10, and also total suspended particles. This also comes with a small gravimetric filter paper. You can collect those particles, total particles, and you can do the further chemical analysis. And we have this condensation particle counter. This is very similar to P-track equipment, which can measure nanoparticles. So the combination of these two will give you the air quality details, how many smaller particles are there and how many bigger particles are there and what is the mass. And we have next range is 10 nanometer to 10 micron. The combination of these nanos, SMPS, and particle sizer can measure particle size range 10 nanometer to 10 micron, which is very useful for all kind of air quality studies. Okay, because the particles, if bigger than more than 5 or 6 micron, they can quickly settle down. So most of the people always use from 10 to 10 micron. You don't need a much bigger size range. And for if you want to do very high-end research, and then definitely you have to go for a gold standard equipment like SMPS and also the APS and the LAS. With the SMPS, you can measure 10 nanometer to 1 micron or 1 nanometer to 1 micron. So there are different types of models in the scanning mobility particle sizers. And we have also generally optical technique. I mentioned that earlier. Below 300 nanometers, optical methods are not very suitable. But with very fine um, technology, we are able to measure even 100 nanometers of these nanoparticles. We have an instrument called laser aerosol spectrometer, and this is this I explained already, aerodynamic particle sizer, which can measure from 500 nanometers up to 20 micron. All these are research grade equipment. And TSI is going to launch Blue Sky in India very soon, because nowadays most of the people are looking at network monitoring to different sites. For example, in night, if you want to measure air quality inside your NIT Calicut, then you can install these low-cost monitors around the fence line, and you can see how these particles are changing. PM values are changing at different locations of in your campus. So I play a small video again, and then I will summarize.
Air quality varies from street to street and neighborhood to neighborhood and changes throughout the day. What is the air quality like when your kids walk home from school? How does the air quality change during rush hour? Does the nearby manufacturing or shipping facility have any impact on the surrounding community? Is my air quality affected from a wildfire in a different area? From the measurement experts, TSI is proud to introduce Blue Sky Air Quality Monitors. TSI has been in the particle research field for over 50 years and is known for precise measurement tools and pushing the industry toward the future. TSI's Blue Sky Air Quality Monitors calculate the air quality index by measuring PM 2.5 and PM 10 size fractions, temperature, and relative humidity. Blue Sky Air Quality Monitors are easy to use and easy to install yourself. Simply log into the cloud to see all the data in real time. No software or mobile apps required. Setting up multiple Blue Sky Air Quality Monitors allows you to create a network of cloud-based monitors that will supply you with real-time air quality measurements across an entire community. This data will allow you to observe trends over time, which can assist with putting plans in place to help alleviate or counteract these emissions. You choose whether or not your data is visible publicly, or if you want to keep it private. You can also set up custom alerts to inform you if there's an issue with the sensor. These monitors contain TSI calibrated sensors, providing data that is more accurate than similar monitors on the market. Our sensors are calibrated to the same standards as TSI's other high-quality monitors. TSI is dedicated to providing accurate data to improve people's lives. The data Blue Sky Air Quality Monitors will provide can help shape future city planning. Steps taken today can improve tomorrow's air quality. To learn more, visit
Yeah, that is about Blue Sky, and we are going to launch in very soon, maybe next month, for Indian customers. So in summary, I can say that if you want to buy or choose any equipment for your research, it should be a project specific, because if you are doing an indoor air quality project, you need a different equipment compared to the outdoor air quality studies. And also it is a location specific. If you are doing any experiment at engine, behind the engine, you need a different equipment compared to a low concentration regions. And also you have to choose right and reliable instrument so that you will get a more accurate data. And another important thing is proper sampling. As I mentioned earlier, relative humidity is very important parameter. And also for number concentrations, diffusion is one of the critical factors. You should have a proper sampling method to measure accurately all the particles or number or size distributions. And you should have to tell about air quality in certain place at certain time, or you need to have enough data and have a good quality data, so that you can assess the air quality of any particular region or any place. Okay, so TSI does offering counter sizers and mass measurement designs for different ranges, size range, or you can call it as a different grades. Okay, yeah. With that, I'm ending my talk. But yeah, thanks a lot for the opportunity, and I will be happy to answer your queries if you have anything.
Yeah, thank you, Ramakrishna, for this very nice talk on this. Almost like I think you have covered almost all the instruments for these air quality measurements, particularly on these aerosols. So I think there are one or two questions, like in the chat box.
Yeah.
Maybe I'll just read out that for you. So the first question is, what is the suitable PM range for human and environment?
PM range, that means yeah, see, mostly there is not we call it as a respirable range, that always PM4, but the particles of PM4 below PM4 to up to 1 micron, up to 1 micron can easily detected by the optical counters. If you want to measure particulate mass, then the range should be from 0.3 microns to at least up to 5 microns, so that you can cover entire but you can measure entire particle mass. But below that, if you want to measure very fine particles mass, then you have to go for a different techniques. That is also, but since they contribute very less mass, people always look at the particle number instead of particle mass. For particle mass, it's always between 0.3 to 5 micron at least.
Okay, so that was a question from Abbas Singh. I hope that it was answered. And another question is, there is one question from Rajendra Kumar Dixit, but I think it is not complete. What are the major sources, or what are maybe Rajendra Kumar Dixit? You can just unmute yourself and ask the question. The question is not that clear.
I'm Ryan Dikshit. Actually, question was that what are the major sources of pollutant, especially in the rural areas? Or second question was also related with that. If I compare the pollutant particle, metallic particle or carbonic particle, which kind of particle are more harmful or more dangerous for us?
For the first question, there are multiple sources. I showed you one graph, one picture here, which is summarized by the Lanker Foundation. So in the outdoor or rural areas, the biomass burning is one of the key issues for the air pollution, because still many people are using what you call wood or cow dung or some other waste from the crop. They are using still for the cooking or some other things. So that is one of the major thing. Also cultivation, the dust from the cultivation is also contributing a lot for the air pollution. Sorry. When you are doing farming, there is another important key thing is from the pesticides. When you are spraying the pesticides, that is also contributing a lot for the air pollution. Basically, if you ask me, these are the three major issues: crop from the crops, and also crop burning, and also from the dust from the farming. And the second question is,
I think the second
metallic
question is,
metal
yeah.
particles cannot go very deep if they are bigger, but if they are very small, they can go very deep into lungs. For example, any metal particles, either lead or some other things, they can even go into your blood. They create a lot of troubles compared to organic, but still that organic part is can be also equally dangerous. Only if the metallic particle is very small. That means a smaller nano metallic particles can create more, can go very deep into your lungs and create a lot of problems.
Sir, I hope your question is answered. And there is another question. Can you mention open source free softwares for air pollution modeling? I think it is not the right question to be asked to you.
No problem. I can
No.
see. I have some fair idea on open source. WF chemistry is one of the nice softwares for the aerosol studies, and in Germany we have used one software that is made for the German researchers, actually made by KIT people, Cultural Institute of Technology. I can share those links if you want later. You can mail me so that I can share you those details. Those are open source, but basically you need good, how do you call, It requires kind of a supercomputer to do the modeling for this aerosol chemistry or aerosol physics. That is the only environment you need. In IITM Pune, they have one cloud computer or supercomputer for these kind of applications. And I don't think anywhere else we have for the modeling studies, in India at least.
Okay. And yeah, so I think this was the poll question. What was the average death rates per day in India due to air pollution in 2019?
Yeah,
And
as per
somebody has
the
missed the poll.
WHO. Yeah, as per the WHO, I just wanted to tell you at the beginning how critical issue it is in India. Almost 1.6 million people were died in 2019 due to air pollution. That was the counted death rate. There will be more uncounted death rate, even more in the rural areas, which were not counted properly. So, so that means almost every day, 4 to 5,000 people are dying due to air pollution.
Okay. So is there any more questions? If there are any questions, the participants, you can unmute yourself and you can ask. There is one in the chat box. Maybe I'll first read out that and then you can ask.
Yeah.
So the question is, what is the temperature tolerance range of the device?
Yeah, different devices have different ranges, but mostly most of the devices have can operate from minus 10 degrees to 40 degrees of the temperature, 40 to 45 degrees.
Okay.
So the other question kindly mention about low cost indoor air quality monitoring devices. So this. So these are all low cost. If you, I don't know what is the low cost. I mean, what is the limit for the low cost? But all these equipment are the low cost equipment. For it's again depending on what for you want for indoor or outdoor. And I can give you more details.
Vignesh Bharati, maybe you can unmute yourself and you can just ask.
So for example, if you are looking for indoor air quality monitoring studies, then all these are very, very less cost. A pipe level of treatment, here you can see that the hose through which it passes from one level to the other, and then finally it will be disinfected and be discharged. Sorry, your voice is very low. I don't know who is speaking, but
Is it Vignesh who is asking or somebody else? Please introduce yourself and then ask.
Good afternoon. Good afternoon, sir.
good afternoon. Good afternoon.
Sir, good afternoon.
Yeah, good afternoon. I can hear you. Please go ahead.
Sir, actually, I'm asking for monitoring in classrooms or another public halls, such types of indoor air quality monitoring devices.
Yeah. So for such kind of studies, if you are looking only for PM, that means only particulate mass, then this is very suitable equipment, dust track. Okay, we call it as a dust track. If you type dust track or any of these, then you can find more details in our website. But this is the low cost PM monitoring. If you want PM including the harmful gases, CO2, ozone, or formaldehyde, some other gases, then you can go for a Q track. Okay, and also if you are measuring, if you want to measure continuously by keeping the instrument inside the classroom, then this is also EVM7 is also one of the options which gives PM and also different gases. So these are the very suitable equipment. Either Q track, dust track, P track, or EVM7. You can choose any one of these. Or if you want bit more research grade or much higher quality, then you can go for this optical particle sizer.
Okay, sir. Thank you, sir. Thank you.
Yeah, thank you.
Any more questions? Mm.
I would like to ask one more question, sir.
Sir, thank you.
Very many times we heard about that this city is very more pollutant or this city is more pollutant. So I would like to interested to know what kind of data used for announce that kind of ranking of pollutant city or pollutant countries.
Yes, in this, I haven't mentioned one region with what people are getting a lot of data, that is satellite data. So in most of the cities, people are using satellite data to check to announce these kind of things. So many satellites can give a day-to-day data of the optical aerosol depth. Based on that, you can by doing some modeling, then you can get a PM 2.5 or PM 10 values, but that is not very accurate. Otherwise, the other method is nowadays. Many for example CPCBs in India are having their own air quality monitoring stations. They are getting the station data every day. So based on that, if we feed that data globally to any server, then they can analyze how much pollution in each city. But what is happening in India is the CPCBs are using, as per the regulations, they have to use BAM or TEOM methods or gravimetric methods, which I showed you in the beginning of my presentation. So those are always overestimates the PM values because they won't take an humidity into account. For example, in Indian context, the relative humidity is always more than 50%. It should be actually, for proper measurements, it should be 30 to 40%. Whenever there is a high relative humidity, then there will be overestimation of the PM values. So that is happening in most of the pollution control boards or most of the places. But it is not the problem of pollution control boards. It's a problem of what we are using and how we are taking the data. But based on that data, we can get the information how much the polluted is in each and every place.
Thank you, sir. And one more thing, I don't exactly know what is the technology term SODAR is saying, but if you have some brief information about that, so please tell something about SODAR. What kind of
Yes,
continuation?
this is another ground-based technique. I never used that particular technique, but I have a brief idea how it will measure. So people use the SODA to measure the optical depth from the ground. This is opposite to what satellite is doing. Satellite looks at down, whereas this SODA looks at up. So it will scan the certain area like a cone. It will scan from one end to other end. It will measure the backscattering light. Backscattering light intensity is always depending on the how many particles are there in the atmosphere. Based on that scattering intensity, it will tell you how many aerosols are there in that, and then you can at the end you can have to calculate or convert that to the PM 2.5 or PM 10. That is another method actually, but the ground-based LiDAR or SODAR methods. But I don't. I mean, in recent days, LiDAR is becoming very popular for the aerosol studies, but very expensive. That's why. But most of the people always try to use these kind of monitors instead of LiDAR. But people like some of the there is a network called RFI network for the aerosol studies. They have these kind of equipment.
Okay, there is few more questions. So one is, sir, out of your experience, can you tell me whether AC hall is better than normal halls for large gatherings?
Yeah. See, it is a simple. If there is a internal air circulation, then that AC mechanism is not good. If AC or air cooling system is taking air from the outside, where I mentioned two things at the end. Just a minute, I will show you some one picture. Actually, this picture was released by this kind of picture. I mean, it was released by German Aerosol Network Society. They did some experiments for this COVID-19 during this COVID-19 in last October. So they found that if ventilation or filtration mechanism is working properly, that means if your AC is having a proper PM 2.5 or PM 10 PM below nanoparticle filter, then there won't be any issues. And also most of the places, the halls, they have recirculated systems. In those kind of systems, it takes air from again and again from the same place. Instead of that, if air is taken from the outside, that will be much better than recirculating air from the inside.
Okay, there is one more question from Bindu. What about the humidity tolerance for laser aerosol spectrometer for measuring outdoor air quality, especially using at places like Kerala where humidity is very high?
Yeah, for almost all kind of aerosol studies, not only it's not specific to the light scattering method, but in general, if you want to have a good data, you should have a relative humidity between 40 to 60%. If there is a more than that, then the particle coagulation will start. They will stick to each other, and particle counting or mass measurements will not be more accurate. So in that case, you have to use a humidity controller or temperature controller so that you can control the relative humidity and temperature of your sample. It's always between 40 to 60 is the best range for the aerosol measurements.
Any more questions? Actually, I have a question for you. It's not related to this one. Now, do you really have now any instruments specifically for this bioaerosol monitoring now? Previously there was this UV APS and recently
UV APS we
stopped.
stopped actually,
Yeah.
but yeah, it stopped due to some regulations inside the US. Only we are able to sell only to US government. We are not allowed to sell outside the US. But we have another equipment called BioTrack, but that is for the very low concentrations. It is not actually meant for the atmospheric bioaerosols. It is meant for the clean room applications. But nobody has used that one for the atmospheric applications. In fact, you can use by using any diluter, but I don't think nobody tried that. And outside TSI, we have sorry.
Yeah, no.
Outside
this BioTrack also, does it works on the same principle of this UV APS?
Yeah, it's also on the fluorescence method. Fluorescence method. Yeah. Not on the time of flight.
Okay. So does it give the number concentration and the mass concentrations as well? Or it just
no, I think it's only number concentrations. Number concentration. It won't give any mass. Yeah.
Okay.
Number and size, I guess.
Number and size. Okay.
Yeah.
And there will not be like any other information on like the type of the particle or other thing. It will just detect the
other problem is bioparticle means it can have any viable content. It can be from virus, or it can be pollen, or it can be anything. It cannot distinguish actually.
Yeah. So you are about to say like some other like other than TSI, there are.
Yeah, there is another company who is selling it's a kind of a LIBS system.
Yeah, the WIPS one.
They have this Bible particle counting system, but I don't know much details about that.
Okay. Yeah, but the managing the data with the WIPS, because it generates huge amount of data with the 3 lasers.
Yeah, that's what I see when I was in aerosol conference in last time in Hong Kong. Yeah.
Okay, okay. And with respect to this aerosol mass spectrometry, like do we get also information regarding the mass of the particles, or it just gives information on the number and the chemical composition?
It will give the mass. I mean, it calculated mass basically, because
Okay.
if you look at this particular technique, it will also measure the total mass of the particles. So because it is measuring size and number, it can calculate the mass easily.
Okay.
It will give you PM 2.5, PM 10, even less also actually.
Okay. So do we get this size distribution as well as the chemical composition?
Size, number, mass, and chemical all at a time.
All at a time. Okay.
Yeah.
And what's the size range of the particles that can be measured using this?
In this, it actually starts from 90 nanometers, I think. From
It
90
is the time of
nanometers.
flight mechanism, right? For
Yes,
the
yes, time of flight. This is these
so can we
both
go up
these
to 90?
techniques are time of flight. Sorry.
Okay. With time of flight, can we go up to 90 nanometers?
90
Size
nano. Yes,
range?
yes, 90 nanometers. You can see these the optics here. It can measure 90 nanometers, but there will be a little bit artifact based on the particle shape. But it can measure for 90 nanometers. This particular equipment, I use this
Okay.
equipment, so it can go.
Okay, okay,
Yeah.
okay. So you said that in India, you have supplied
See,
it to
you might be
IIT
confused. I'm
Kanpur?
sorry. I would like to explain you here.
Uh-huh.
Here, time of flight mass spectrometry. This is for the mass spectrometry analyzing, not for the particle sizing. So particle
Okay.
sizing also we have another two lasers
That is
here.
another laser
Huh.
for the particle sizing, and for the chemical characterization, you have another laser.
Yes, there are two
Okay.
time of flight regions here.
Mm-hmm.
Yeah.
The same like the one in the UV APS for the fluorescence detection. Here for
Yes,
the
yes,
chemical
yes,
analysis, you have a separate laser.
yes.
Yeah. So in India, where do we have this instrument?
Single particle mass spectrometry nobody is having.
Nobody's
But
having. Okay.
AMS is with IIT Kanpur and at Professor SNT Sir lab, and also
Okay. SNT
IIT
Patil sir's lab?
yeah, Tripathi Sir
Yes,
lab,
Patil
and
sir. Uh-huh.
in IITM Pune, Tara Prabha madam has this
Okay, okay.
this one, and also PRL they have a mass spectrometer.
Okay.
Only
PRL
these three
Ahmedabad,
places, as far
they
as
have?
mine.
Okay, okay, okay. Thank you, Ramasamy. So from the participants, is there any more questions? Okay, I think there are no more questions from the participant side. So Ramasamy, can you just give me that presenter option?
Yeah. Yes, yes, please.
Okay. So this is just an announcement to the participants. So for the participants, you can just attend this poll to just mark your attendance. So it's not just like any kind of quiz. Just for your attendance purpose, you can just attempt this. And Ramasamy, Ramakrishna, thank you very much for this very nice presentation. Actually, like getting to know about these many instruments in just one talk, usually it's very difficult. So you have
Yeah,
very well explained all
I'm
these
sorry because
different instrumentation techniques.
yeah, content wise it
Yeah.
is too much, but if you have any specific doubts or if you need any specific information,
No,
please.
usually like everyone will be having a lot of confusions in choosing the right instrument for
Yep,
their
yeah.
measurement purpose. So your talk was very much helpful in like clarifying those things and like getting people introduced into the new techniques that are available for this aerosol machines. Thank you very much, Ramakrishna.
Thank you, ma'am.
From the
Thanks a lot.
organizers part and from the and on behalf of the civil engineering department, I thank you. Yeah. So
Thank you very much. Thanks a
anyway, we'll
lot.
be
And
getting in touch with you like for
sure,
the
sure.
instrumentation.
Yeah, sure. Thanks.
Yeah. Thank you.
Thank you, ma'am. Bye. Shall I leave now?
Okay, you can leave.
If you have any, anyone has any questions,
Is there any more questions? If anything more is there, can ask.
Okay.
Okay, I think there is no more questions. Okay, thank you, Ramakrishna.
Thank you, ma'am. Thank you. Thanks a lot. Thanks from TSI.
Yeah, thank you.